Hello everyone, welcome to this week's video. Today we're going to be talking about our power systems. So this is going to be just a general overview of our power use for both the orbital module. So this is the stage that will bring us to to Mars from Earth, and then we'll retain an orbit and do communications, and also the probes themselves. So let's start off with the probes themselves. So we have a couple different power draws. So we have our computing. So this is going to be the flight computer. Eventually I plan on organizing this better, but since this is updates on the project itself, this is not a final. Everything, of course, is in change. So computing, so this is just going to be our flight computer again. I don't really expect it to draw more than a watt at any given time. Sure, there's going to be instantaneous power, but I realistically think that this is more of our duty cycle more than anything. Because it won't need to compute a lot of things that would be super strenuous, like a control system, because it's not going to be active for the majority of the time. So we have our main communication system, which is the main UHF system, which again is 433 megahertz. And then you also have COM2, which is our LoRa system, which is the experimental backup system. And again, LoRa isn't really meant for this, but it's a decent backup, and I think it would be applicable. And of course our GNC system, that's going to include things like any reaction wheels and our sensors and our cameras and stuff like that. So the actual probe instrumentation is counted in GNC. Of course we need to actually heat the probe itself to maintain the temperatures within the probe. So we have heaters, and of course we're going to assume a basic charging loss for standard and alternate power. We've got a power factor of 0.9. Well, it's just a general factor of saying we're 90% efficient. So it increases it by 10%. So we've got different power modes. We have 4 different power modes. Our standard power, that's what we're going to spend most of our time in. We're going to do alt power. The only real difference between these two is which communication system we are using. I have it clarified in here, but we assume that it's 6 minutes per orbit, and again, that's part of the duty cycle calculation. So it's about double the power for the 3 watt as opposed to the LoRa system, which is a 1 watt system. It's also important to note that the main UHF system has a higher data rate than LoRa, so even though it's 3 times the power, it's only double the power usage over 6 minutes because of that higher bandwidth. So we don't have to communicate as long to transmit the same data. Then we have low power mode. This low power mode is activated at 50%, I believe. And so it just reduces our biggest power draw, battery heating system, in our computing. So that means that it'll do less offloading, and it basically has a very basic uplink between COM2 just to say it's okay and this is its battery and any basic data at the time. So it's not like over a course of a period, it's literally active. So like whatever the exact temperature, pressure, things like that are at the moment. And we'll scale back the computing time for COM1. Survival mode, you might see that it's actually higher in computing, and that's actually to heat up the CPU on the computer a little bit more, because we have decreased that heating again by half. So again, these are just lower values. So we can see instantaneous, we can expect about 5.2 watts, 5 watts, 2.6 watts, and 1.6 watts in each of the respective modes. So not that big of a power draw. and I'll be talking more about the battery selection probably next week. So then the basic orbital module power draw. So we're going the same computing, COM1, COM2. We have an RF amp because our transceivers are not the main power source. And then we've got our GNC sensors, reaction wheels main, backup, battery heating, and charging losses. I currently don't have that in the calculation because the panel size that we have is about 30% extra than what we actually need. So it's not really a concern at this moment. So computing, because we're going to always have an active GNC system, because we will want to point towards Earth and point towards our probes, we will be using a pretty consistent 20 watts. This is also just an extra redundant system because we'll have a secondary compute unit. So each compute unit will be about 10 watts at full tilt. And then our communication system. So COM1 in this case is our X band, but it can also be UHF. It's very flexible in its design. And the same with COM2. We'll also have multiple antennas inside the probe for high gain and low gain. You gotta create that redundancy because missions like Galileo truly prove that you need that. So with COM1, it has 100 watts of RF power. And yes, I do understand that the power usage is going to be higher than the RF power. Again, the orbital, this calculation is very much rough. I'm just showing off where it is in its current stage. All power, it's just going to do 50%, low power 0, and in eclipse orbit. So this is when we are saying that it's in the eclipse period, so it's not generating any power. So we don't have the survival mode as we do on the probes. We're going to say 100 watts and say that it's communicating with the probes. So COMS2, it's much lower power. It's only a 10 watt transmitter. And again, it goes to 50% at all power. RF amp at full tilt is 200 watts at this moment. Again, 50% reduction. And at low power, it does quarter reduction. So it's only at 50 watts. Our sensors are going to retain at 5 watts. This is way over what we would ever expect. But I expect some heating for them to maintain their use for clips and redundancy because of radiation. So we have a main set of reaction wheels. This will actually be able to orient the spacecraft in space. And the reason we have a main and a backup is the backup is going to be basically a copy of what we have on the reentry module for the probes. So they're going to be super small, which means their slew speed, which is the time it takes to go in between angles of the spacecraft, it's going to be very, very long. And they're very low power for that. But the main reaction wheels have a much faster slew rate, which is better for tracking and stuff like that. And they draw 100 watts at full tilt. So, low power is a combination. Yes, I understand eclipse. Eclipse is just standard, pretty much. It's just no sun. And so we've got our totals here. So we can say that at full tilt, we can expect about 500 watts of power. And currently, I believe the panels are designed for 600 watts, and that is for in general, so that's over eclipse. Sorry. And then that's also to include the degradation expected over the mission timeline for the panels themselves. Because of course, you can't have exactly the amount of power you need at the time that you start, because A, you're going to be at Earth, so you're going to generate more power, and the cells haven't started to degrade. So that's pretty much it. I will keep you updated on the power system. I want to do more about the power architecture system, the computing architecture system, but that will be a later video. Thank you very much for watching. Have a good day.